Good morning. Any questions or any comments? A quick recap. So we are trying to solve mean field BCS Hamiltonian, and it is given by this C dagger C and C dagger CC, which is like a quartic Hamiltonian, and we used mean field decoupling to reduce this quartic Hamiltonian to quadratic form. Let's C dagger C, CC, C dagger, and then we wrote this Hamiltonian in like a matrix form and introduced something called Nambu spinner. And then we showed how we do the Bogolubov transformation for this after some manipulations, and we found that the Bogolubov quasiparticles are defined by this B, which is written in terms of original electron operators C and C dagger, and there's another one. So this is for Bogolubov quasiparticle operator for spin up, and this is for again Bogolubov quasiparticle for spin down. But I think we have to be careful because this new Bogolubov quasiparticle is a combination of up and down spins, right? But more importantly, it is like a combination of a particle or like an electron-like term here with hole-like term, right? So we have like a coherent superposition of electron and hole states because of this C and C dagger, and also here, and they have like canonical anti-commutation relations, and we verified those, and then that means our excitations are fermionic. And we said now we need to see how these Bogolubov quasiparticles behave with the BCS variational BCS wave function. So let's do that. Any questions or any comments? So I want to consider psi BCS as written before. So this is product over all k. Again, this is a vector, but I'm not writing not to clutter too much. So this is UK plus VK, CK up dagger, so C minus K down dagger, and all of these are acting on vacuum zero. And that's the difficulty, right? The BCS is written by original electron operators, but the B's and B daggers which diagonalize the Hamiltonian are not C and C dagger, right? They are like coherent superpositions of C and C daggers.
What is the mean field rather than BCS?
So this one is this one is BCS wave function, right? So this is not technically this is not mean field. So when we say mean field, we mean things like this. So there's like this quadratic term, and we decouple this quadratic term, like this is the mean field, right? And after the mean field, there's like a mean field, if you want, like potential, which is called sometimes pair potential. But the Hamiltonian is like C's and C daggers in the field of this psi, which is free electron, and then this delta is like pairing potential. But BCS is different beast, right? BCS, so this wave function, you can even use it on Hamiltonians that are not mean field. Technically, I wouldn't call it mean field, right? This is like this is like a correlated state, and correlated in like a very specific way. You want to take into account all kind of pairings. So the goal is to see what B, for example, K up does to this psi BCS. And as before, there is like a product of all K's, but the only non-trivial contribution is going to come from this K index. Whatever this K index is, just pick up the same index from this product and carry out the commutations. And that's what I'm going to do. So bk up we define here, and we'll be using this plenty. So this thing, let me copy. And this thing is going to hit on this. So this is UK, need some space. So it's acting on UK plus VK, C dagger, C dagger. This is K up, this is minus K down, acting on 0. So I have this UK, this term, and VK, CK up times this thing. This is the first piece, plus, let me open up some more space. And there's this term, right? This minus VK, C minus VK UK, C minus K down dagger. So this one and this one. And lastly, this minus VK squared, C minus K down dagger, C K up dagger, C minus K down dagger, acting on 0. So all of these, like they're all acting on 0. Now this one is also like, right? So this minus K down and K up, they commute. So they are going to pick up a minus sign. There's no problem with that. And I can make this minus plus. What about this product of 0, right? Because you cannot create two fermions there. So this is 0. All we have is this term and this term. And this term we need to commute, right? This is, we want to put all the C's to the rightmost side so that they can hit on 0 and give us 0. So this is going to be 1 minus CK up dagger, CK up. And if I multiply with this, this is going to be C minus K down dagger, and this is C minus K down dagger. And this one, right, this is K up minus K down. They can just commute and pick up a minus sign like this. So I carry it here, and this is becoming plus. Now this C is on the rightmost side, and hitting on, it's going to just give 0. What remains is, so this is UK VK C minus K down dagger minus UK VK C minus K down dagger, but this is something minus the same thing. It's going to give us 0. Good. Since B minus K down dagger is exactly the same, I will not do it, but I can do it if you want. So so this is B minus K down, acting on psi BCS is 0. I mean, they look trivial, but it's sometimes not trivial. So this is, let me give you as an exercise for you. And this, right, let me also write this as an equation. So this B K up, acting on psi BCS 0. And these two identities are telling us psi BCS is the vacuum state of this mean field BCS Hamiltonian. So then psi BCS is the vacuum, if I can spell it, vacuum state of mean field BCS Hamiltonian. So we have like a very non-trivial vacuum, but nevertheless it is the vacuum. So this is what we are going to build, or excitations. Therefore, like vacuum is like zero energy. There is no energy in the vacuum, and over this vacuum we create so-called excitations. Right? Exactly like harmonic oscillator. Like the philosophy is like we have like a harmonic. Let me just remind you. So this is h bar omega, a dagger a plus a half, and vacuum is defined by if you hit with a, it's going to give zero. Right? There is nothing in the vacuum, and anything you put above this, like something like a, there is like some normalization. So this is like now not vacuum, right? This is like what we call it like one quanta state, and corresponding energy is h bar omega 1 plus 1/2. So we are going to do exactly the same thing, but with this more complicated setting. So this one, we call it exactly like here, we call it one quasi-particle state. We can have B, K, up, dagger acting on this vacuum, or we can have B minus K down. Right? We can, because we have two different creation and annihilation operators. Each can create a different kind of quasi-particle. And the energy of this thing is epsilon of k, and energy of this thing is E of k. And we found this Bogoliubov spectrum. So these are called superconducting Bogoliubov quasi-particles. And the energy, let me also write you what they were. This is like psi of k squared plus delta squared. And this one too, right? They have the same energy, because psi of k is h bar squared k squared over 2m minus mu. Mu is the Fermi level, or the chemical potential, and psi of k is equal to psi of minus k. So both of these quasi-particles have the same energy. And so at t is equal to 0, right? And the fermionic statistics is going to require us to think a little harder than that. So this is bk dagger bk up. Okay, first at t is equal to 0, there is no quasi-particle, right? The tricky one is at t is non-zero, and in that case we know from Statbeck this is going to be Fermi-Dirac distribution times whatever the corresponding energy is, and in this case it's E of k. Okay, because since B are fermionic, and this, let me write if you forget, Fermi-Dirac of x is equal to 1 over e to the beta x plus 1, and beta is equal to 1 over kbt. So after the diagonalization, we have also expectation value of b minus k down, b minus k down dagger, because of this Nambu spinner, right? One row is C, the other row is like C dagger. That's why one quasi-particle comes like B dagger B, the other one comes like this when we diagonalized. And this can also be calculated exactly, right? You just commute, and this is going to be 1 minus F Fermi-Dirac of epsilon of k. But in the calculation of like order parameter, which I also started calling it like pair potential, delta was equal to, so this g squared sum over all k, expectation value of c k up, c actually minus k down, c k up. So the tricky thing about this is like this is written in terms of original electron operators, right? C and ck down and ck up, but our Hamiltonian is diagonal and the expectation values are defined in terms of b dagger b's. Now we have to convert from c to b dagger b, and that's the inverse Bogoliubov transformation. We did the transformation here. So we have bk up and b minus k down. Now we need an expression for ck up and ck down in terms of b's, right? And that's also very easy to do. Let me just quickly show you how to do that. So this Bogoliubov matrix was u minus v, v star, u star. So this is the Bogoliubov matrix we had, and if you take Hermitian conjugate, it is going to be u star v minus v star and u, and this is 1 by using u squared plus v squared is equal to 1. So this is u dagger, this is u, and here you can remember in that calculation, I think I just saw it a minute ago. So here bk up, b minus k down is equal to u dagger times ck up, c minus k down. So I'm going to write this and then invert. So this is, okay, where is, okay, so this is u dagger times ck up, c minus k down dagger is equal to bk up, b minus k down dagger. Now if I multiply both sides with u, so this is u, so this is u dagger u is 1, then I can write an expression for c in terms of b and b dagger, and c k up, from here I can read what it is. It is going to be u star of k, right? U star b k up plus v, so this thing v k of b minus k down dagger, and similarly c minus k down dagger is equal to yes, I think that's correct. So minus vk star b, I'm multiplying this with this, b k up plus uk b minus k down dagger, uk b minus k, okay, dagger. Okay, good. Then what we want is we want to calculate the expectation value of this c minus k down, c k up, and since I have this, it's going to be a little bit quicker. So this thing is expectation value of c minus k, and I need to take Hermitian conjugate is like this. So this is dagger, this is u star, and this is no dagger, times ck up is again defined. So this thing and close the expectation value. And here you can see we have minus what do I have? Minus uk star Vk, expectation value of Bk up, dagger, Bk up. Right now, B dagger is quasi-particles in the diagonal basis, so this is good. So B dagger is going to be non-contributing, right? Because right, this is, and the second contribution is going to be so B dagger gone. So BB is gone, and this one, last one is plus UK star VK, expectation value of B minus K down, B minus K down, dagger. Good. And now we can use what we just found. So this is minus UK star VK. So this one is F Fermi-Dirac of epsilon of K, and this one is minus. So I think what we found was like 1 minus, right? Minus 1 plus F Fermi-Dirac of epsilon of K, and this becomes, if I push 1 inside, this is UK star VK 1 minus 2 FD of epsilon of K. Good. Then I can put this in the expression for pair potential, or like delta. It's going to be G squared sum over all K times this expression. Now this is like a temperature dependent gap equation, right? Previously we didn't have any temperature dependence. Okay, now I want to talk about the solution. We did a lot of derivations, and now the physics part comes. So let's first think about the spectrum. So this E of K is equal to psi of K squared plus delta squared, and psi of K is h bar squared K squared over 2m minus mu. And at Fermi level, right, mu is defined by this, okay, Fermi surface is defined by this h bar squared K Fermi squared over 2m is equal to mu, right? This is, whenever this happens, this is the last occupied state, and that's the Fermi level. Then at the Fermi level, this is going to vanish. So let's see how the spectrum looks like. So let's say this is K, and this is K Fermi, right? And first, let's take this delta is equal to 0. And what happens is like, so this is E of K. What happens is like I have two branches, right? This is also like plus or minus, because we found two eigenvalues. One was plus, the other was minus. And with delta is equal to 0, I have these branches like this, okay. So this is like that. So this is like that. And so this one is delta is equal to 0, right? So I go towards the, right, at the delta is equal to 0. This is equal to absolute value of psi, but there is like plus or minus. And as you approach the Fermi level, you go to 0. And plus one becomes minus and continues like this, and the other one turns like that. Right? Is that? Yeah, it is like in the vicinity of Fermi level. Like if you look a little bit further away, it's going to bend. But we are only interested in like a small window around the Fermi surface. In the around the Fermi surface, you can linearize it, right? It is lowest order term is linear, but there will be like parabolic curve. So what is important is this is gapless. There is like no gap, and that's what we expect for metals, right? For metals, for K bigger than K Fermi, this psi of K is bigger than 0, and we call this particle excitations. And K less than K Fermi, psi of K is less than 0. This is like negative, and we call this Hall excitations. And the picture is something like that. So you have some Fermi surface like this, and inside you are fully occupied at 0 temperature. And you can do two things. You can either create, right? You can take a particle from here. When you take this particle, there is now like a hole here. So this one is hole. And if you put that particle you take above the Fermi surface, this is like particle or electron. Sometimes people call it electron and hole. Some people call it particle and hole. So this is particle or electron. By the way, this is exactly like the Dirac equation, right? In the Dirac equation, you also have like a vacuum, and there is like excitations above the vacuum and excitations below the vacuum. And below the vacuum, you have negative energies for these holes, and above you have positive energies. And we have exactly the same thing in the vicinity of metals. Good. Right now, there is no superconductor. This is like simple metal. Now we are going to turn on this delta is equal to non-zero. So these are normal. In superconductor, delta is non-zero. And what is going to happen is because of this, right at the Fermi level, psi is 0, epsilon is delta or minus delta. As a result, so I have either this parabolic dispersion or this parabolic dispersion. Right? So this is delta non-zero. And the excitations here, the excitations are C and C dagger. Here we have B and B dagger, like these B operator, Bogolubov amplitudes. And for epsilon of K bigger than 0, there's like a quasi-particle excitation. There's like a gap. At least, right? You need at least an energy of delta here. Energy delta.
For superconductors, we said that delta different than 0.
Yes. Yes. So this is delta non-zero. Yes, thank you. And for negative energies, we have quasi-hole with excitation energy at least minus delta. And now in the metal we had like a gapless state. In the superconductor we have like a gap. For particle hole excitations, gap is of order 2 delta, right? That's the minimum energy you need to pay to make any excitation in a superconductor. So this is what we call energy gap, one of the most important quantities in a superconducting state. And so just a little side note, if you remember in the Landau criterion of superfluidity, we were saying that we are just putting like a linear, let me use another line. We were using like a linear line, right? Something like this. And if this line intersects here, that's like the critical velocity. And we also have like a superfluid here, and this linear slope is like lambda critical velocity, and it obeys the definition of a superfluid. So superconductors are also superfluid from like a Landau criterion viewpoint. Whereas if we had like a parabola like this, right, the critical velocity would be 0. Because of the gap, it's shifted, and there's like a finite critical velocity, which is non-zero. So I want to go back to these B's and B daggers again. Let me copy. So this is okay here. Let me copy the whole thing. So you can see, so the B and B up and B down, these are like Bogoliubov quasi-particles. They are written in terms of C and C dagger. And if you look at this piece, so this is electron-like piece. So this is electron-like contribution in quasi-particles. And so this piece, if you look at these amplitudes, they are multiplying C daggers. And C dagger is opposite of electron, which is going to be hole-like, right? So this is hole-like contribution of quasi-particles. And the amplitude of, these are like, these are coherence factors at U and V. The amplitude, the probability to be in the electron-like state is, U, this is the amplitude, and probability is like a square of this. So this is amplitude is U of K, or probability UK of absolute value squared. And similarly here, amplitude is V of K, or probability is Vk squared. This is usual interpretation in quantum mechanics. And if you remember these nice expressions we derived, so it was like U or V, let me write, I can copy, UK was equal to absolute value, so 1 minus, I think this one plus psi of k divided by E of k, and Vk was defined like with the minus. And if you look at how they change across the Fermi surface, so here's let's say this is my Fermi surface, and so this is UK or VK. Let me use blue for UK. You can see UK so deep inside the superconductor. So let's consider the square of them. Like this is UK squared, so this is VK squared. So deep inside the superconductor, this I think Vk is a little bit easier to okay, let's consider Vk. Deep inside the superconductor, epsilon of k, and okay, so this is epsilon squared plus delta squared, and okay, let me draw and try to make sense. So this is, I think, inside, this is like hole-like, because this is hole-like. Let me use hole color. So this is going like that and going like this, right? This is Vk squared. By the way, you can just put them in a computer and plot. This is what you are going to get. And the other one, it's like very small inside the superconductor, whereas it's going to go like this. So this is UK squared. So this is hole. So this is electron. Good. Any questions? Let me do this one last solution. I think this is one of the typical results of BCS theory, and after that I can finish. I have at least show it to you. So self-consistent gap equation. So here you can remember this delta was equal to g squared sum over all k. I think we just calculated it. Let me not do it again. So this is u star vk, and this is 1 minus 2 f Fermi Dirac of epsilon of k. And this thing is, right, this thing is 1 over e to the beta x plus 1, and you can rearrange here, and it's going to be a tangent. So this is g squared k uk star vk. So let me write, I'll write everything at the end. So this piece, I think it can be trivially written like tangent hyperbolic beta over 2 epsilon of k. Just use this Fermi Dirac function, right? 1 minus 2, and then you multiply both sides with e to the beta epsilon, and this just plays out nicely. And this piece is 1 over 4, right? We just wrote this. This times this is going to be 1 minus psi squared over e squared, and this is 1 over 2 e squared minus psi squared is delta squared. When it goes out of square root, it's going to be delta divided by e squared out of square root is going to be e. Then this thing delta is equal to g squared sum over all k 1/2 delta over ek times tangent hyperbolic 1/2 beta e of k. So this is the gap equation, but temperature dependent, and that means we can, for example, extract things like Tc from this equation. So let's write this equation, and let me show you how different limits are obtained, and then I'll finish after that. So this is, we'll do the usual thing. So for constant delta, I'm assuming there's like a constant delta everywhere in the superconductor, so this is going to be cancelling this, and I'm going to have just 1. And this sum over k, we have usual prescription, so this is d psi goes from minus h bar omega d pi to plus h bar omega d pi, and there's density of states at the Fermi level, and this thing, so we called BCS coupling constant lambda. So okay, let's write this. So this is lambda, actually 1 over lambda is equal to, and I can because psi is even in k, epsilon is going to be even in k, and I can go from 0 to omega d pi and multiply with 2, and this 1/2 is going to go, then it will be something like this, from 0 to h bar omega d pi d psi 1 over psi squared plus delta. It looks like we cancelled delta, but there's still delta inside E, and this is going to be tangent hyperbolic 1/2 beta psi squared plus delta squared. And the job is for a given temperature, okay, let's also write this. This is 1 over 2 kBT. This is the only place we have temperature. For a given temperature, we can solve this equation to find delta, and it's going to give us delta versus T. So that's the job. So let me do two things and I'll finish after that. First, let's determine TC. So if you remember, we had a long discussion about this at lambda Ginzburg theory. At T is equal to TC, delta, what is delta supposed to be? Right at the transition temperature? Zero, right? Exactly. And from here, we can put TC and find TC for this expression. And it is, okay, let me write this. It is something like 1 over lambda is equal to from 0 to h bar omega d pi. Let me shift just a little bit. And this is d psi 1 over psi, right? Delta is now 0. And I put tangent hyperbolic 1 over 2 kBt. Delta is 0, so this is psi. And I want to define this 2 kBt here and 2 kBt here, and this is 2 kBt. And that equation becomes
It's just T over TC.
So this is TC, absolutely, yes, very important, thank you. So this is exactly at TC, delta is 0, right? So this is TC, and these are all TCs. Then let me define something like, so this is x, dx, this is x, this entire thing is tangent hyperbolic x. And the limit is going to be, let me call it x d pi is equal to h bar omega d pi over 2 kb tc. This is also tc, so let me call it, so this is tc x d pi. And this integral is a little bit divergent, and there's like a way to make these divergent integrals regular, and it's like a long story, but let me show you how basically you can, as long as you make something infinite finite, it's fine, right? And people call it regulation. And then you can even make a course out of it and talk about it for 6 months, called renormalization. But here I don't want to do that. I just want to get something finite out of this. And the way I found is, so you just do the biparts, right? So this is, because if you do it this way, it first diverges as x goes to 0, right? This is, and but this one is not the problem. So this is x goes to 0, but tangent hyperbolic also goes to 0. The bad part is as xt goes to infinity. As xt goes to infinity, tangent hyperbolic is going to 1. So this is 1 over x, and it's logarithmically divergent. And typically logarithmic divergences are good. So we like logarithmic divergences because they are denormalizable. And but without getting into that, let's just talk about how we can treat this. So this is dv and this is u. I'm going to do biparts, and it's going to be log x times tangent hyperbolic x from 0 to xt. Right? If I put xt, it's going to be log xt. And for very large xt, tangent hyperbolic is approximately 1 minus from 0 to xt dx log x. And so the derivative of the tangent hyperbolic is 1 cos squared x. And if you put this in Mathematica, it blows up. And somehow if you put this, it doesn't blow up. I think they, my guess is in their code, they went and put like a line for this kind of expression because this is kind of famous. Because you also need to regulate this. But I mean, it gave me a finite result. If you give me finite result, I'll take it. So, and it is this piece, Mathematica gave me, it gave me so-called Euler constant, gamma, plus log pi over 4, right? From here, I can tell they actually put like a case and said, if this is the integral, just give this result. I think that's my guess. And this part is log XD. And if you combine everything, this becomes
Hocam, is this integral, I mean, the answer is independent of x?
it's supposed to be independent, but unfortunately it's not, right? So XT is what? XT is h bar omega dBi, and we are saying omega dBi is like 300 Kelvin, and kBTC is a fifth Kelvin. This is supposed to be a very large number. But for a very large number, you want this to be convergent, but it is logarithmic. Unfortunately, it doesn't converge.
But I mean, we put the integral limits from 0 to x dBi, and I mean, the answer has no x dBi. So
Yeah, there is x dBi here, right? Here, log.
in the right.
Oh, yes. For this part, I take the limit x dBi goes to infinity, yes. For this one, so you just need to take a large x dBi limit. That's what Mathematica gives. Good. Then let me combine everything. This is log, so this is xd. I'll combine this like e to the gamma and times 4 over pi, right? So this minus is going to make this plus, and it is minus, and I made it like 4 over pi. Then I think so this is equal to 1 over lambda. Then e to the 1 over lambda is equal to h bar omega dBi divided by 2 kBTC times e to the gamma, this is Euler constant, times 4 over pi. And if you rearrange, so this kBTC becomes, right, this is a number, this is rather famous result, 1.13 h bar omega dBi times e to the minus 1 over lambda. Good. So a second thing, I think if you need to leave, you can leave. I want to show one last thing and then finish it there. So there's like a second thing is like to solve this equation at t is equal to 0. And that equation becomes a little simpler. So this is like, let me just write it, 1 over lambda is equal to, from 0 to h bar omega dBi. So this is, at t is equal to 0, tangent hyperbolic, right? If you close to 1. That's why there's no tangent hyperbolic, and this is going to be 1 over and at t is equal to 0, we have like maximum value of gap, which I call delta 0. So this is psi squared plus delta squared, and this integral can be taken. So, and it is like something like arc sine, Mathematica gave me something like that, arc hyperbolic h bar omega dBi over delta 0. I also did dimensionless integral, and at the end I have something like delta 0 is equal to, so h bar omega dBi over sine hyperbolic 1 over lambda, and it is approximately h bar omega dBi 2, because this is 1/2, there's like sine is e to the I, e to the x plus e to the minus, and so this is e to the 1 over lambda. And the result that BCS confirmed, which was also confirmed experimentally, was delta 0 divided by kBTC, right? Here there's h bar omega dBi and e to the minus lambda. Here I also have h bar omega dBi, e to the minus lambda, and they are going to cancel nicely. And I found, let me just write, so this is 2 h bar omega dBi e to the minus 1 over lambda divided by 1.13 h bar omega dBi e to the minus 1 over lambda, and this is equal to 1.76. So that's the famous result in BCS paper, and there are like many good superconductors, they give very close result to this. You just find TC and you look at particular excitation gaps, you take the ratio, and it is independent of any of those macroscopic details. And that's a good way to confirm your theory with experiment. So lastly, this gap equation actually can be solved numerically, right? For like for any delta and TC, you can solve it, and the behavior is something like this. And this is last thing I promise. So this is T, so this is gap. At T is equal to 0, you have this 1.76 kb Tc, and it goes like this. And this is Tc. So this is, if you want, this is a little bit, I mean, I solved it, but it take a little bit of effort. It's solved numerically as an exercise. Good. All right. Thank you. Sorry for taking extra time.